Jnanam paramam dheyam. Knowledge is supreme.
Welcome back. So, today let us try to see certain facts about semiconductors and how they can be used to produce some useful devices. Particularly, we have to see how that would be useful for power electronics. Now, when we talk about solids, a very good definition which really helps us relate the microscopic properties of a given material to the macroscopic or external properties and characteristics of a material, the definition of resistance is very helpful. Now, let us just see the definition of the resistance for a minute. R is equal to rho L over A, where I have just assumed that it is a rod, let us say made up of some metal or maybe some other material, semiconductor or maybe an insulator, I do not know. I have just taken a general example. So, this area what you see is A and this length is L. Now, if I want to determine what is the resistance offered by this rod or this bar of rectangular cross section to a current that is trying to flow. So, let us say there is a current that is trying to flow through this bar and come out like this. What is the resistance that would be offered to this current? This particular expression for the resistance gives us exactly that. It actually tells us what is the resistance offered by this rod to a current that is trying to flow through it. As you can see, area of cross section, L, the length of this bar, these are the physical properties. And these are all externally measurable, observable properties. So, looking at this definition, we have constant of proportionality, which is the rho, which is also called as resistivity. Now, this resistivity is a function of the internal properties of this bar or the material which comprises this bar, which makes up this bar. Now, talking about the resistivity and the resistance, the solids, the solid material can be divided into three main types, and that is roughly based on the resistivity value. So, you have basically one particular category of solids which have extremely low resistivity. So, the rho is 10 raised to power minus 5 ohms meter. This is the typical resistivity that we have for one category of solids. There is another one whose resistivity is extremely high. It is in excess of 10 raised to power 5 ohms meter. And lying between these two ranges is another class of solids which has typically resistivity ranging from 10 raised to power minus 5 to 10 raised to power plus 5, and mind you the units are ohms meter. So, basically what we see here is that looking at the basic definition of the resistance, we can see that any current or any charge carriers that will try to flow through the bar that we have considered in our example, okay, it will see a very low resistance when it is passing through this particular category of solids. It will see a very high, very high resistance when the charge carriers are trying to flow through this type of solids, and here it is going to be in the in the intermediate range, in the intermediate category. It will be, the resistance will be actually modulated. So, basically it will depend on some external conditions that will apply, that they will be, the charge carriers would experience a resistance that will vary between a certain range. So, maybe R1 to R2, between this range. Now, it is customary to actually call these solids, which actually offer a very low resistance to the flow of charge carriers, as metals. And it is very common for this, the other extreme category of very high resistivity, very high resistance, as insulators. And in between these two, this intermediate category, it is common to call this as semi-conductors. Some people also call them as semi-metals. So, semiconductors. Now, examples of metals, of course, there are many: copper, silver, gold, and so on. Insulators, again mica, quartz, and so on. And semiconductors, as we will see, there are many, again there are many examples, the most common being the silicon and the germanium, which are the pure semiconductors in the pure form. Okay, but then there are also certain compounds, like for example, we have the gallium arsenide, or we have the cadmium telluride, or we have the cadmium sulfide, and so on. These are the inorganic compounds of which are having semiconductor properties. And we also have organic semiconductors, like several organic polymers which are there. So, organic semiconductors as well. Now, to understand the properties in more details and then try to see what is the relevance and usefulness of the semiconductors, let us go back to a very fundamental concept, the concept of Neal-Bohr's atom. Okay? So, we all know from what we have studied in our earlier classes that as per the Neal-Bohr atom, the atom's nucleus lies in the center and is having all the positive charges, the protons inside. And around this nucleus are revolving several electrons. Okay? Just like the earth revolves around the sun, these electrons are revolving around this nucleus. And if I just mark these electrons as E1, E2, E3, then I can say that each of these electrons, okay, they occupy a unique orbit, they occupy a unique position, a unique orbit around the nucleus, which uniquely determines the energy of these electrons. So, unique energy. And we all know from our past knowledge that we can uniquely define each of these electrons which are revolving around a nucleus by using the concept of quantum numbers. So, we all know that there is principal quantum number, there is azimuthal quantum number, and so on. So, each of these electrons can be uniquely represented by a set of these 4 quantum numbers. So, each of them has a fixed energy. Now, when an electron, let us say E1, gets some energy from outside. So, let us say there is a packet of energy which has come and hit electron E1. So, let us say a photon which is the fundamental particle postulated by Newton as what the light consists of. The dual nature of light, people know that light has dual nature. It has both the particle nature as well as a wave nature, as proposed by Huygens and the other scientists. So, let us say that the light is falling on this atom, and let us say there is a photon which has got an energy which is more than a certain threshold energy associated with this electron. So, if that energy is transferred to E1, this E1 will move on to a higher energy orbit. So, it will absorb this energy. So, let us just say this is delta E which has been imparted to E1, and E1 will just move on to from position x to x dash, a new orbit that corresponds to the a different energy which is a higher energy than what E1 was associated with at the previous location. Likewise, if let us say E3 loses energy, it will fall. So, it actually this E3 it actually loses energy. So, let us say delta E, it will fall down from its original location y to y dash, to a lower energy. Now, both these energy transitions what we have seen from lower energy level to higher and from higher energy level to lower, the transition from lower to higher energy or from higher energy to lower energy. So, this is what is the concept that we get from the Niels Bohr's atom, the model that he postulated. Now, the point is that the way we look at the Niels Bohr's atom model, it is like an isolated atom we are looking at. We are not talking about the interaction of these electrons with some of the other electrons that might be present in the vicinity. And this is what really happens when we talk about solids and maybe liquids and gases, because then we are talking about several atoms which are coming closer to each other. Of course, in gases this closing in or the distance between the atoms is very large. In liquids it is relatively less as compared to the gases, but still very much higher than what it is there for solids. But for solids, we have many of these atoms, they come very close to each other and they form a crystal structure. Now, we know that how these various atoms are arranged, as you can see, in space, occupying very fixed locations and a pattern which is repeating. Now, these are the atoms, and now if we consider each of these atoms having the same model as what we discussed some time back about the Niels Bohr's atom, then we find that it is not possible for us to really see what is happening, because there are some electrons which are revolving around all these atoms, and we do not know how they will interact, and it is extremely complicated. So, the best way to look at this situation that arises when the solids are formed, that is when the atoms come closer, is by way of the concept of band energy. Now, when we say band energy, what we mean is that let us say we just talk about solids, what we mean is that we will just try to define, we will just try to kind of ascertain the charge carriers and their energies and put them in various categories. So, let us say how we can do that. So, in the band energy concept, if I have the energy which is plotted here in the y direction, okay, then I can, if I just maybe divide this in certain zones. So, let us say I just define this in these 3 zones, and I just say that this is a zone which is having further divisions. Okay. Now, this is energy, your y axis is energy. So, basically you are talking about various energy levels here. Likewise, in this band, which I have not yet mentioned what this band is, though I am sure many of you can guess. Again, let us say there are several sub energy levels, and there is this band here which is in the middle of these 2 bands, okay, which is, let us say, does not have any charge carriers, it does not have any electrons or holes. Okay. So, this band what we are calling, which is sandwiched between the top and the bottom band, is what is called the forbidden band, which basically means that none of the charge carriers, electrons or holes, are going to occupy this band. Okay. Now, all the electrons, if you look at the basic diagram here, where we have shown so basically there are these atoms which are lying very close to each other, and we know that some of the electrons here are sticking very close to their parent atom, they are sticking very close to it. So, let us just say that those electrons which are very close to their parent atom and not free to move, let us say they are lying in this band. Okay. Let me just call this as A band, this is B, and let us call this as C. So, C is the one which is forbidden, we have seen. A is, let us call this as valence band. So, these are basically, this band will contain all the electrons which are kind of stuck with their parent atoms, they are bound to them and they are not free to move. Likewise, B, the band which is shown at the top here with the higher energy level, is called a conduction band. Is called the conduction band, and this consists of charge carriers which have been actually transported from close to the atom. They somehow found some energy, maybe thermal energy, which then helped them to kind of jump over onto this band. So, all these green lines, they are showing how the charge carriers, when they are in valence band, okay, but when they are imparted energy, they somehow find energy, they are actually transported, they are actually all going into the conduction band, and there in the conduction band they exist as free charge carriers and they are free to move. So, basically this is the basic concept of semiconductors, and as we go along we will understand this even better. Now, inside the semiconductor, these charge carriers, they are in constant motion back and forth. So, they will find some thermal energy, some of these carriers will actually be able to jump over this forbidden band and will now become a free charge carrier when it goes to the conduction band. When they collide, they lose energy, they actually then fall back. So, I could probably say that they are coming back here, back to the valence band, where they combine with holes and get neutralized. So, this process is all the time on. At temperatures greater than the absolute 0 temperature, it is possible that some of the electrons, they find enough energy to break away from their covalent bonds and become free. Now, electrons from vicinity may then come and occupy these missing electron positions, and similarly we may have more electrons coming in and occupying these latest missing electron positions, and the process goes on. So, it would seem that as electrons are moving towards one direction, the missing electron position, which we have also called as hole, is moving in the opposite direction. Now, at thermal equilibrium, the densities of electrons and holes are same. Let us say this density is Ni. Then this is governed by a very important relation, which is Ni squared, which is the square of the density of either the electrons or the holes, is equal to C, where C is some constant of proportionality, e raised to power minus q e g by kT, where Eg is nothing but the band gap energy and is equal to 1.1 electron volts for silicon. Q is the magnitude of the charge of the electron, K is nothing but the Boltzmann constant, and T is the temperature in degree Kelvin. Okay, so what is the situation though in the conduction band with this? Now, it is observed that in metals, even at room temperatures, there is a huge amount of charge carriers which are there in the conduction band, which we have marked as B, and that is why the metals, copper, silver, gold and so on, they show an enormous conductivity even at room temperature. And once you have applied an external electric field, these charge carriers, they will just flow as per the field and you will not be able to control them. There is no control. Now, if you look at the insulators, which is the third category that we considered, you will find that the conduction band has very few charge carriers, and in fact there will hardly be any charge carriers, and hence when you try to apply an external field, there are no free charge carriers to move around, and that is why you will see an insulator conducting very less current. It will hardly have any current. Now, semiconductors on the other hand, which lie between the first and the third categories, the metals and the semiconductors, they actually have a very unique property. They actually present, as we will see now under certain conditions, very unique opportunities to allow controlled flow of charge carriers. We can actually control these carriers. So, let us just see now how this is achieved and how useful semiconductors are formed. Now, as we expect all our electronic circuits, for which eventually we are going to use many of these devices made up of semiconductors, we expect them to actually be operating at room temperatures. Now, the semiconductors at room temperature, I am talking about in their pure form, silicon, germanium and many of those, they actually have few charge carriers available or present in the conduction band at room temperature. In fact, at absolute 0 minus 273 degrees centigrade, in principle there is 0 charge carrier in the conduction band of a semiconductor material. Now, what do we do? Now, that is at this point and here that we introduce what are called impurities in these semiconductors. So, let us understand this phenomenon of adding impurities in the semiconductors. So, I have, let us say, a semiconductor solid block, and we know from the band theory that there are 3 layers, 3 levels. the valence band, and the forbidden band where no charge carriers can be present. They are not allowed to occupy any of the energy levels here, and the conduction level. We know this. Now, what we do with some technique, we try to bombard the semiconductor solid, okay, with an impurity. There are many trivalent or pentavalent impurities. Now, what I mean by this is trivalent, like for example boron, okay, or aluminium. So, if you look at their outermost shell, if we talk about we just talk about the Niels Bohr's atom as an isolated atom, and if you look at these elements, and there are many more actually in this group, then what will happen? These guys, they have 3 electrons which are there in the outermost shell. And if you are trying to basically bombard this material with what are called pentavalent impurities, pentavalent means something like phosphorus and arsenic and so on, these guys, they have 5 electrons in their outermost shell. Okay? So, let us say this is the situation. Now, what happens when we bombard these trivalent impurities here on this sample? What happens? Let us see that. Now, this particular sample, okay, the original semiconductor, which is not adulterated at all, you have not mixed anything with it, it is a pure semiconductor. We also call pure semiconductors without any adulteration, without any mixing, as an intrinsic semiconductor. So, we have this piece of intrinsic semiconductor, and we know that, let us say we are talking about a silicon semiconductor here. So, we are going to have this is the situation. So, silicon, 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 and silicon, silicon, silicon. And we can see that the outermost shell of these silicon atoms, they have 4 of these electrons, and they form covalent bonds. They form covalent bonds with their neighbors. So, let us just see the case of this and this atom, these 2 atoms. So, you can see that there are 1, 2, 3, 4 electrons around this silicon, and there are 1, 2, 3, 4 electrons across around this silicon. So, what these 2 atoms do, they are the neighboring atoms of this crystal structure, they form what is called a covalent bond. Okay? There are other types of bonds also, as we know, ionic bond for example, but that is not what we are discussing here. They are not relevant to our semiconductors. So, likewise, this silicon atom, it can form a bond here with a neighboring, which is at the bottom below this, can form a covalent bond there. Likewise, it can form a covalent bond here, and likewise it can form a covalent bond here. So, it is basically these 2 electrons, these 2 electrons, these 2 electrons, and these 2 electrons, they are shared, they are constantly interacting, they are just going back and forth, and they are just. So, this is a theory which has been given for the covalent band which are formed. So, this is how the intrinsic semiconductor or silicon semiconductor structure would look like. Now, on that you bombard your trivalent, the boron or aluminum. What would happen if you have actually many of these atoms bombarding here at this place is that these atoms, they will go and maybe they will dislodge one of these or many of these at different places silicon atoms. So, what basically you will have is a B coming in here, a B coming in here. Okay. Now, what will happen that when the B comes here, because it is one electron short, it has got 3 electrons in its outer orbits, it is actually having an affinity to have another electron. So, basically what happens that it actually will pull out one electron from some atom in its vicinity. Now, that when it moves and it completes the the boron's valency requirement, but it does it at the expense of basically extracting one electron. So, this electron let us say move here, and when it moves here it basically leaves out what is called a hole. So, as you can see, this electron is gone there, leaving a missing electron position or the hole. So, many of these atoms of the boron trivalent impurity, when they actually replace the atoms which are originally sitting in the intrinsic semiconductor, they actually generate many such missing electron positions or the holes in this entire structure. Okay. So, such atoms like the boron, these are called acceptor atoms or acceptors, or this is called an acceptor type impurity, because it accepts an electron, okay, and generates a hole. Now, when many of these trivalent atoms are added to this structure becomes rich in holes, and because the hole is missing electron which we associate with a positive charge, therefore, this entire structure becomes rich in positive charge carriers and is called a p-type semiconductor. It is an extrinsic semiconductor now, but a p-type semiconductor, an extrinsic one, the one which has been adulterated, which has been mixed with impurities, or in terms of semiconductors we call them as doping. So, it has been doped. An intrinsic silicon semiconductor has been doped with trivalent impurity to generate p-type semiconductor material. Now, likewise, in the same way, it is easy for us to see that if a pentavalent or atoms with 5 electrons in their outermost shells, when they are going to be mixed with the intrinsic semiconductor, okay, then at that time we are going to have the atoms which will go and sit and replace the original silicons, they are going to have one additional electrons. So, these are called donors. They actually are able to very easily donate their electrons, and these electrons then become free to move, just like we have the holes becoming free to move in the p-type semiconductor. Here we have electrons which are free to move, just because these pentavalent atoms have acted as donors and have donated several electrons in this material. Okay. So, this kind of semiconductor, this is called an n-type semiconductor. Even after doping, the thermal ionization process, which causes the breaking of bonds, is not disturbed. This is because the doping concentration is much less, compared to the intrinsic semiconductor concentration. Therefore, even after doping, the product of the thermal equilibrium densities of the electrons and holes, which we now define as N naught and P naught. So, their product N naught P naught, it still remains equal to the square of the intrinsic densities of the hole and the electrons. So, we could actually write N0 P0 equal to Ni square. Now, this is a very important relation, and it is also called the law of mass action. Okay. So, we will see now in the next lecture what more we can do with these semiconductors and how we can form some useful devices with them. Thank you very much for your attention.